513 Graham's law of effusion and diffusion. For the worksheet, do numbers for, if you're in general chemistry, do 1, 2, 3, and 4. And then do 2, 3, and 5 if you're in for AP. I didn't write that down for the general. Now, first I just want to jump back and look at some things that are here that come before that. In 510, it mentions, well, actually, yeah, 510 talks about the kinetic molecular theory. And at a later date, I'm going to go through that material. It's more conceptual. But kinetic energy equals 1/2 mv squared. That's an important equation you're going to see pop up. The kinetic energy of an object is 1/2 times its mass in kilograms times its velocity in meters per second. Now, see, normally we think about speed or velocity in miles per hour. And we talk about weight, like pounds. But when an object is moving, obviously it has energy. And you know this if it collides with something. Think about that, like a small car might collide with something, or a large car might collide with something. And a small little like Volkswagen, those old Volkswagens, or a real heavy 18-wheeler truck. Obviously, the truck has a lot more energy if they're going the same speed. Just say they're both going 55 miles per hour. If they crashed into something else, the truck's going to have a lot more energy, a lot more kinetic energy because it has much greater mass. Anyway, we'll come back to that. And then in 511, the definition of the word in temperature, a measure of the average kinetic energy of the particles of a substance. That's important. If you put a thermometer in hot water and just say it was 99 degrees Celsius, or you put it on your mouth and it said you're about 37 degrees Celsius, that's about normal temperature for a person. 98.6 they say, but 37 Celsius. That 98.6 is Fahrenheit. Or say you also put it in like maybe, let's see, hot water. What about in the air? And the air temperature was just like 27 degrees Celsius. Well, all we're saying is, just say this might be air, this might be a person's body, this might be hot water. Where are the particles? Where do the particles have the most kinetic energy? Well, it will be in the hot water. Because the way it's a combination of their motion and how fast are they going and how big are the particles. And as they collide, 99 is a way to measure that average energy that they have. Well, in the air, 27, that would be pretty cool compared to that. That would be going the slowest of all of these on the average. And here, the particles will be moving somewhere in the middle. Now, of course, it's not just how fast they're moving, but it's also how massive they are. So, it's depending on these two things, you'd have to check. But I can tell you that the particles in the air, they're not going to be as massive as I believe like your blood particles moving through your body. So anyway, okay, so kinetic energy measures that. Well, now we get to, I believe it's Thomas Graham, law of effusion and diffusion of gases. What do we mean by the word diffusion and effusion? Now, in your notes, I know the old ones say 613. Mine says 613, but it's 513. How do we jump to 6? The process by which a gas spreads throughout a space to fill it is diffusion. You know about this already. If you were to open up, just say you have someone's cleaning in the kitchen or in the bathroom, and they open up, and you walk in there like, oh my goodness, they're using bleach. And you can notice it from just, a long way off in the other room. You start to come in and you notice it in the air, and you get stronger and stronger as you go in. Well, just opening up bleach, a bottle of bleach, there's gas that is going to evaporate, and we know that it slowly vaporizes and it slowly fills up all the air around it, all the space around it. Okay. This is true for anything, not just bleach. Perfume would do it. Can't think. What's another? Well, I'll just stay with perfume or maybe like a bleach, something like that would move out and fill up the space. One thing interesting is that gas molecules are always going to they're always going to fill up the space. Remember, I mentioned once before that you can imagine, like from Avogadro's law, that there are a limited number of parking spaces for gases. Equal volumes of gas at the same temperature and pressure have the same number of molecules. Well, if I were to saturate this with gas, I can just have whatever, I don't know, I didn't calculate it too good, 4 times, about 5, 1, 2, 3, 4, 5, about 20 spaces here and there. So I can only have 20 molecules in this area, and I could have 20 in this area as well. Well, when they spread out, they spread out homogeneously. O-U-S, homogeneously. That means that they're also equally distributed throughout the air. So all that tells you is, well, like I can do it here, like you're going to have a molecule on the average, like say every, whatever it is, maybe, I don't know, let's just pretend every inch you'll have one molecule. We'll just say that for every square inch you'll have a molecule. Or I should say cubic inch, really. You'll have one molecule for every cubic inch. That would mean that they're homogeneously spread out. Now, one gas, that might be true, but say that in the room you have oxygen and you have nitrogen, okay, and you have carbon dioxide. Well, the most abundant gas is actually nitrogen. So if this were oxygen, then you would have a whole lot more, just like the red would be nitrogen. Nitrogen gas molecules would be a lot more frequent. You'd see maybe, we'll just make it up. This is not true actually, but I'm just gonna kind of make that up and say you'd have more. But the point is, it's still, the two gases are still spread homogeneously throughout the space. That's an interesting thing about it. So you're not going to have all the oxygen on this side and all the nitrogen on this side. Because of their random motion as they keep moving around, it's going to homogeneously fill up the space. So diffusion is the process by which you may have heard of this as well in biology class. You go from, they'll say, from an area of greater concentration to lesser concentration. But all that means is this. Let's just say that in this bottle, I'll just make it a little bit easier. Say that in this bottle we had these gas molecules, and we had all these nitrogen molecules in here, and let's just say we had all these oxygen molecules in there with them. They can both be inside there. Maybe it was pressurized chamber. Yeah, it would have to be probably. So like a pressurized container, and you opened it up, and now the gas comes out. Well, see, what happens is they're gonna keep coming out. Oh boy, they're gonna keep coming out, and then little by little, they're gonna keep moving around randomly to fill the space up until it's homogeneously throughout all the space. So in other words, all the air will be like this. It will all have the same number of oxygens for every cubic inch, and the same number of nitrogens. At that point, everything is homogeneous. Everything is evenly distributed. Evenly distributed is a good way to define that. Evenly distributed. Okay. All right. So that's what happens. You go from a high concentration that spreads out to equally fill up the room. All right. Now, so what Graham noticed this. He talked about, well, some gases diffuse and they come out faster than other gases. Okay, why is that? He found that it was based on the density of the gas, or another way to be worded is on the molar mass of the gas. And it says, here's what his law reads as: at the same temperature and pressure, the rates of diffusion for different gases are inversely proportional to the square root of their molar masses, or their densities. He actually stated his law in terms of densities. So the rate of diffusion or effusion is inversely proportional to the square root of the gas densities. Now, I didn't mention what effusion. Effusion is the same thing It's just like effusion is more of a controlled way to measure it, perhaps. Like, say if I have a small opening in a can and the gas comes out, well, it would be the rate of diffusion of gases, the rate that it comes out through an opening. Or like even if you open up, like say a tire, you press the tire, you press the valve, how fast it's coming out. That would be counted as effusion, effusing out. It's just easier to control and get that as well. Because you think, how can I measure diffusion? Well, you open a container up and you think, well, when I smell it, that would pretty much tell me how long did it take to get to me. It's spreading out through the whole room, but effusion is more like coming out one opening, one space. Just know that they're the same there. Now, his law, actually, it comes from this concept of kinetic energy. And here's the idea behind it. Remember, at the same temperature and pressure. So if you're at the same temperature, if two gases have the same exact temperature, then that means they have the same average kinetic energy. And I'm going to show you how to get his equation, and I'm going to give you the equation afterwards. So let's just say I have two gases. I have gas A, kinetic energy, and I have gas B. Now, what I'll do next is, I know that kinetic energy is 1/2 mv squared. So, half of the mass of A times the velocity of A squared, that should equal 1/2 the mass of gas B times the velocity of B squared. All right? Now, the next thing, I can take 1/2 from each side and I can just cross that out. I don't need that. So MAVA squared equals MBVB squared. Then, what I can do is I'm going to divide both sides by by the mass. So I'm going to say divide this side by the mass of B. I'll do this in a few steps to show you. That side by the mass of B. So that way it goes away. And then here I've got mass of A times the velocity of A squared over the mass of B equals the velocity of B squared. Now let's divide both sides by the velocity of A squared. Okay, so that'll go away and that'll go away. So the mass of A divided by the mass of B equals the velocity of B squared over the velocity of A squared. Now, let's get the square root of both sides. I'm going to have the equation a little bit opposite, backwards there. So the square root, can you see all that? The square root of the mass of A over the mass of gas B is equal to the velocity of gas B over the velocity of gas A. Now, when you take one gas velocity divided by another, you're finding the rate. It's a ratio. What's the ratio of the velocity of B to velocity of A? Like if you divided the velocity of one car B, divided by the velocity of car A, and if you divide car B's speed or velocity divided by car A, and it comes out to be 5, that would tell you that car B is moving 5 times faster than car A. If you divide those two numbers and you got like 0.5, then that means, oh, A is moving faster and B is moving like half the speed of that. Well, anyway, that's a side thing. This is actually Graham's law. Now, one way to write it is, as I showed you, we write the other way around. Actually, we normally write it this way. I have the letters kind of, this would certainly work, but I'll say the velocity of gas A over the velocity of B equals the square root of the molar mass of gas B over the mass of gas A. So we said inversely proportional. That just means that the other side, A's on the top, B on the bottom, but here you have B on the top and A on the bottom, and you got to get the square root of that. Now, it used to be on the AP, they put R for rate, and they use molar mass of B over the molar mass of A. Now, if you use density of E over the density, that also works, because since they're at the same temperature and pressure, then and their volumes are also going to be the same in there as well. All right, so let me just go with this. I'll just go with this one. And there's one thing interesting as well, but I'll just for now I'll just keep it at that. All right. So if you really wanted to do these problems and you didn't have the equation or you didn't remember the equation, just remember Graham's law says 1/2 mv squared of gas A equals 1/2 mv squared of gas B. So if I put in mass of A, velocity of A squared, I'll get mass of B times velocity of B squared. So you could let that be your equation if you wanted to, just to remember. But here are the equations for Graham's law. Either one of those. I'll go with the top. All right, so here's what we'll do. First, and yeah, I see 1 and 2 on the paper instead of A and B, so it could be the same deal. Letter A, first problem. A sample of chlorine gas effuses 0.311 times as fast as an unknown gas. Calculate the molar mass of the unknown gas. Now, one thing I did not bring up yet, and I just remembered, and I should have told you this in the beginning. So, if two things have the same kinetic energy, 1/2 mv squared equals 1/2 mv squared of another. This is gas A, this is gas B, okay? Well, think about this. If A is a really, really big car, like a truck, like an 18-wheeler, and its mass times its velocity is equal to the mass and velocity of a small car, like let's just let this be a little baby smart car, okay? Well, how can that be true? How in the world can they have the same amount of energy? Well, think about it. The smart car's velocity has to be different than the 18-wheeler's velocity. If they have the same, if these two numbers are equal, we'll let that be MB and VB and MA, VA. If these two things are equal, which one has to be moving faster? It would have to be the smart car. It would have to be going very, very fast in order to have the same energy, like imagine impact, as an 18-wheeler. I mean, so an 18-wheeler just barely has to move at all. Okay, just say if they're going to run, say that they ran into like a, well, we won't make it a tree. I don't want to be dangerous, but say they ran into like a stop sign, and they did stop, but they ran into the stop sign. Okay, well, if they both ran a stop sign and they did the same exact impact, same exact damage to that thing, the 18-wheeler just barely has to roll into it, and it will knock down. That smart car has got to be going a little bit faster to knock it down in the same way the 18-wheeler, to bend it all the way down to the ground, we'll say. So the bottom line is a small particle, smaller particles have this faster speeds. They're moving at a higher velocity. So in the room right now, wherever you are, the number one gas in the room, the most abundant, is nitrogen. 80% of the air is nitrogen. And about 20% is oxygen. 32 is the mass of oxygen molecules, and nitrogen is 28. So the nitrogen are smaller. So what does that tell you? Which particles must be moving faster? Since they have the same, in the room, they have the same temperature. They have the same average kinetic energy. Everything in the room is the same temperature wherever you walk around with a thermometer. So these would have to be moving faster speed than these are. So the smaller one's moving a faster speed. Okay, I'm sorry I just didn't mention that, and I'm going to get back to this now. A sample of gas effuses 0.311 times as fast as an unknown gas. Calculate the molar mass of the unknown gas. Okay, so we'll start with the equation. Mass of B over mass of A. Always remember to flip those. Now, I like to customize this equation for your particular problem. So, we're comparing two gases, chlorine gas, and don't forget it's Cl2, and unknown, UNK gas, we'll call it, UNK. Now, the rate, we don't know this. This is just something you might want to write down to help you. It says chlorine effuses 0.311 times as fast as the unknown. So 0.311 times the unknown's rate of diffusion. So we'll let the unknown be moving at speed x. That means chlorine will be moving at 0.311x. Now, you don't have to write down this, but it's just something in your mind you might want to think. You might want to write it down to kind of help you. All right, so now let's plug these in. So I'm going to say the velocity of chlorine gas divided by the velocity of the unknown gas will equal the square root of the molar mass of the unknown gas divided by the molar mass of the chlorine gas. They have to be crisscross from each other. Remember, Graham's law says they are inversely proportional to the square root of the molar masses, or the square root of the densities. So so chlorine is moving at 0.311 x, and the unknown is moving at x. The unknown, the mass of the unknown, we don't know. We're trying to find that out. The molar mass of the chlorine, okay, we'll go on the periodic table. Chlorine is 35.45. 35.45, and you have two of them, Cl2, that becomes 70.90. Don't forget the Hofsprinkle, 70.90 gram per mole. Now what I'm going to do is I'm just going to work on the math to find this. Now, you notice I didn't even really need these x's because they're going to cancel out. But I just did that to kind of help you kind of in your mind organize it. I mean, if we said chlorine was effusing 5 times as fast as the unknown, chlorine will be 5x, and that will be x. And you don't even need the x's. You just need the rate is 5. So what we're saying is the rate of this divided by the rate of that. That's the relative rate. So 0.311 equals, all right, what I'm going to do to both sides, I'm going to square both sides. If I square this side, I'll square that side. That way I can get rid of the radical. So 0.311, squared. Sorry, I wrote it down before I told you what I was doing. 0.311 times is 0.0967. Okay, equals, now we lift the radical, the mass of the unknown divided by 70.90. Now what I'm going to do is I'll cross multiply 0.0967 times 70.90 equals 6.86 is the mass of the molar mass of the unknown. It will be gram per mole. That is a crazy small mass. Maybe something that Vela made up, because it doesn't seem like there will be a gas that's that light. Maybe something like lithium, well, close to lithium. Maybe lithium vapor. Lithium vapor might have a molar mass of that. Okay. All right. So that is the first one. That's A. Now for B is kind of going backwards in a way. It's going to say, well, now we're going to tell you what the gases are, no unknowns, but we're going to ask what is the relative rate of diffusion. What that means is, on B, well, let me read the question. Calculate the relative rate of diffusion for H2O and NO gas. Calculate the relative rate of diffusion for water vapor and nitrogen monoxide gas. Okay. The answer to the question needs to be something like this. H2O diffuses at blank times as fast as NO gas diffuses. That's what they want. So they want you to, what we did on A, what we told you on A, they want you on B now to kind of go backwards and find out what that answer is going to be. So again, we're going to customize the equation here. Now, let me think. It's good if the one that has a molar mass, if the one that's larger is on top, it might make the question a little bit easier to state your answer. I'll show you what I mean. So H2O and NO, which one has a higher molar mass? Well, H2O, you probably know, is 18.02. Nitrogen monoxide is 14.01 plus 16. It's 30. So it's the heavier one. So I'll put the heavier one as B, and I'll let H2O be the other one. So the velocity of H2O divided by the velocity of nitrogen monoxide will equal the square root of the molar mass of nitrogen monoxide over the molar mass of H2O. You do not have to do what I just did a moment ago and put the heavier one on the top under here. You don't have to do that. I'll show you why I did it in a minute, okay? It doesn't matter. If you put, the only thing that matters is if H2O is on the top here, then H2O should be on the bottom on this side. If NO is on the bottom here, it needs to be on the top on that side. That's the only thing that you have to do. So, what you're actually going to find out, you're going to plug in these numbers that I just mentioned a moment ago. The molar mass of nitrogen monoxide is 30.01. On the chart, you add one nitrogen and one oxygen. And nitrogen monoxide has no color. It is colorless. No has no color. It's one way to know that. 14.01 plus oxygen is 16. That's 30.01. H2O, I've told you many times, memorize it. Add one O plus two H's, it's 18.02. Now, when I divide that out, I'll just do it here. 30.01 divided by 18.02. It's the square root of 1.665. And then if I actually get the square root of that now, 1.290 is the answer. So, the velocity of H2O gas compared to the velocity of nitrogen monoxide gas is 1.290. What that means is water vapor, H2O, water gas, diffuses 1.290 times as fast as nitrogen monoxide. You need to make a statement like that in your problem. Okay. Water vapor diffuses at 1.290 times as fast as nitrogen monoxide does. Now, okay, what if you had done this problem and you put NO on the top and you put H2O on the bottom? What if you flipped it? Well, then that means these will be flipped, so your answer will be the inverse of what you got there. So your answer will be this. In fact, there's a button on your calculator that looks like 1 over x, an inverse button. And if I have 1.290 on my calculator, if I just take the inverse, where is that 1 over? Oh, there it is. On my calculator, it's really crazy. It's the second function above that one. But if I push shift and 1 over x button, I get 0.7752. So, you can also say that nitrogen monoxide gas diffuses 0.7752 times as fast as H2O. Okay, you can also do it that way. So which way is right? Well, if I don't specify it, either one is okay. But just know that when you're doing your worksheet, as long as you state this one, I mean, if it's 1.290, you just state it that way. If it's 0.7752 for your answer, you just state it that way. Whatever's on the top diffuses this many times as fast as the one on the bottom. Okay, so that means it actually goes slower. 0.7752 is slower, and that one, H2O, goes faster. That makes sense. Okay, the smaller molar mass. Okay. Now, there's only one more problem, and if you're general, you do not have to worry about this problem at all. You can just move on. But for AP, I will do it. And let me see here. All we're doing is showing you what happens when they actually give you the speeds of each one. And it says on C, I had A up there for a while, I guess. In an experiment, hydrogen gas effuses at 15 milliliter per minute, and unknown effuses at 200 milliliter per minute. What is the molar mass of the unknown gas? Oh, this is not hard at all. So hydrogen and unknown. Now, if we want to try to figure it out, it doesn't matter. It doesn't matter which one goes on top and bottom here. So velocity of hydrogen divided by the velocity of the unknown is the square root of the molar mass of the unknown divided by the molar mass of the hydrogen gas. Hydrogen gas, H is 1.01 on the chart. So that means H2 is 2.02. Oh, what am I doing? Vela. Crazy Vela. I'm sorry. I was putting in the mass and I was putting in the wrong place too. I'm just doing too fast. Okay. 15 milliliter per minute is hydrogen's 15 milliliter per minute divided by, and what's the other one? 200 milliliter per minute. 200.0. So, equals the square root of the mass of the unknown we don't know, and now I can put in my 2.02 gram per mole there. Because I was just so excited to write that down, and I had to put it already there. I tried to, okay. All right, so 15 divided by 200 is 0.0750 with sig figs equals the square root of the mass of the unknown. Chalk is going, as you can tell, over 2.02. Now, what I'm going to do is, and it's gram per mole, but it'll be gram per mole for your answer. First, you square both sides. So square this side and square that to get rid of the radical. So 0.0750 squared is a really small number. It's 5.63, 10 to the negative 3 is equal to the mass of the unknown divided by 2.02. Now, I'll just cross multiply times 2.02, and oh my goodness, are you kidding me? This is horrifying. I made up a horrible example, I guess, or got one. Probably I have the numbers backwards or something in the problem when not when I did the problem here, but I did right, didn't I? 15 milliliter per minute, and the unknown is 200. 15 for hydrogen, 200 for the unknown. Okay. Oh yeah, that makes sense. Probably I should change the question around for the future, but anyway, I did it right. But it makes sense. This unknown gas moved a lot faster than hydrogen. And hydrogen is like the lightest gas on the periodic chart. So anyway, that's the answer I get, 0.0114 gram per mole. So, oh well, that's the way you do it mathematically, and there's nothing wrong with that. It's just that the problem that is kind of crazy. Did I get this out of I don't know if I got this out of a book. If I got it out of a book, what happened was I probably flipped these two numbers because anyway, hydrogen diffuses very fast. But that's the way you do it. No gas will have a molar mass less than 1. Okay, so, well, not that we know of now, at least. Not anything we know about at all here. Okay, so that is all. So just work those out, and thanks, you guys. Sorry for this goofy example. Well, I'll see you, though. But that's how you do it, though. I'll see you later.